And we're back. So on today's show, we take you back into high school geometry. We're going to go into the Euclidean plane, and we're going to remember a couple of theorems that dominate high school geometry's treatment of circles. We're going to talk about central angles and inscribed angles, tangents, secants, power of a point in this screencast. That's our plan. So here we go. Just to refresh us on vocabulary, take a circle. Here's the center of the circle, usually denoted O. An angle whose vertex is at the center of the circle and which intersects the circle in two places. This thing is called a central angle for fairly obvious reasons. An angle formed by two chords that meet on the circle. Two chords crossing on the circle. This is called an inscribed angle. Now, you may or may not remember from your work in high school that an inscribed angle is half the intercepted arc, half the degree measure of the intercepted arc, whereas a central angle is equal to its intercepted arc in measure, degree measure. Well, it turns out that the inscribed angle is half of what we would call the corresponding central angle. And if you did high school geometry for any significant length of time, you had the picture of here's a central angle, and here's an inscribed angle with those two endpoints there, and whatever this was, this had to be half as big, because an inscribed angle is half the measure of its corresponding central angle. Well, it turns out that that proof is true without even talking about degree measures. I mean, that is true whether or not we associate the degree measure of an angle to the degree measure of an arc on a circle. So there are three cases to consider. I'd like to consider all of them. The measure of an inscribed angle is half the measure of its corresponding central angle. I will sketch this. I will sketch this in a very basic way. Very basic way. Three cases to consider. The first case is the case where the angle is on a diameter. One of the rays is on a diameter. So we're going to assume that QR is a diameter, O is the center of the circle. We'll just assume that for argument's sake. So the inscribed angle is this angle, call it alpha. What I want to show is that angle POR, the corresponding central angle, is 2 alpha. And the way we do that is not terribly difficult. This is an isosceles triangle because OQ and OP are radii, so that's alpha. And then this angle is an exterior angle to this triangle, and in Euclidean geometry, this angle is equal to the sum of the remote interiors. Yeah, that's 2a. Similarly, what happens if I have some inscribed angle PQR and the center is in the interior of angle PQR. Well, if that's the case, then we draw in the diameter, one of whose endpoints is Q, and we're looking at this angle and this angle. And I'm trying to show that if the inscribed angle has measure alpha plus beta, that the central angle has measure 2 alpha plus 2 beta, and that's not too hard. Again, isosceles triangle, so that's alpha, that's a nice exterior angle. Isosceles triangle, so that's beta, that's an exterior angle. So no trouble there either. And there's a third case to consider. And that third case is the case where I have some inscribed angle PQR, and O is not in the interior of that angle. So we can still draw the diameter. Maybe the other endpoint is S. I'm looking to show that if the inscribed angle is gamma, that POR is 2 gamma. That's the basic idea. So let's pretend that that's delta. I mean, why not? Then, since OQ is congruent to OP, this up here is gamma plus delta, which means that this angle out here is 2 gamma plus 2 delta. Except we know from the first case that based on this diagram, that's already 2 delta. And so this has to be 2 gamma, and we're done. So the whole idea where an inscribed angle is half in measure of its corresponding central angle, that's a fairly big deal. We exploit that in our future. The other big theorem that we're going to take a look at is the so-called power of a point theorem. The so-called power of a point theorem. And that just means I take any circle, I take any point that's outside the circle, or for that matter, inside the circle, really doesn't matter. I take any other point. Any point that is not on the circle. Draw the line. That line hits the circle at 2 distinct points. The power of O with respect to the circle is the product OQ times OR. This distance times that distance. If the line I draw only intersects the circle one time, if that's a tangent line, then we define the power of the point O to be OP squared. What I will ask you to prove is that the power of a point is well defined. That is, no matter where I put O, and no matter how I draw the line, the power is the same. So you have to show that if I draw a circle and I pick my point O in somewhere in the interior of the circle, and I draw a chord like this, and I draw a chord like this, you have to show that OQ times OR is equal to OS times OT. You have to show that. I imagine that similar triangles is going to be the key for you. Similar triangles is going to be the key. You have to show that if you choose some point outside the circle and you draw a secant like this and you draw a secant like that, that OQ times OR is equal to OS times OT. And again, similar triangles will be the key for you. You will be able to do that. You just have to draw in the right segments to get triangles that are in fact similar. Because when I see products like this, I think that these came from proportions. And when I see things that look like they came from proportions, I think things like, oh, there must be similar triangles involved. So those are some things that you should consider. And if you come to class ready with that, you are in great, great shape. Just saying. Just saying. Okay, so that's going to be that for now. Those are your big theorems from high school geometry. The power of a point and the relationship between central angles and inscribed angles. And that's all for now, and I'll see you tomorrow with this stuff hopefully well started.